Hi, welcome to today's talk on projectile motion. What are we learning? We're going to learn how to calculate the range of an object in projectile motion. When looking at projectile motion, we need to look at the vertical and horizontal motion completely independently. The vertical motion is just free fall. The horizontal motion is constant speed. Let's take a moment and watch the two vectors that represent horizontal motion and vertical motion. Notice that the horizontal motion does not change. The vertical motion is just like free fall. This figure shows an experiment illustrating the independence of the horizontal and the vertical motion. The gun's aimed directly at the ball the instant the target is released. In the absence of gravity, the projectile would hit the target because the target wouldn't move. However, the projectile still hits the target in the presence of gravity. That means the projectile is falling through the same vertical displacement as the target despite its horizontal motion. The experiment also works when you set it up as this image here in this multi-flash photo, when the initial velocity has a vertical component. So in this example, you can see that vector A can be described as the sum of the vector A sub x and A sub y, the x component and the y component. Now let's do a little trigonometry review. The cosine of this angle, if this is a right triangle, is the adjacent over the hypotenuse. To find this a sub x, or the x component, we just solve it for a sub x. We'll do the same thing for sine, which is the opposite over the hypotenuse. Solve that for a sub y. Finally, the tangent of theta is the opposite over the adjacent. And we just use the Pythagorean theorem to find the relationship between the x component, the y component, and the magnitude of our original vector. The most important fact about projectile motion in two dimensions is that the horizontal and the vertical motions are completely independent of each other. This means that the motion in one direction has no effect on the motion in the other direction. So imagine tossing a ball along a path here shown. We'll find the y component, the original y component, and the original x component, and these two will be independent of each other. Now imagine tossing a baseball along the path shown here. The motion in the y direction is going to be just like you threw the ball straight up and down. The motion in the x direction is going to be just like you threw the ball and it went at a constant velocity. Let's look at an example. Let's say we're going to take a picture of a ball in projectile motion going along this path at 1 second intervals. We're showing the horizontal component and the vertical component. The vertical component starts at 30 meters per second, and the vertical motion is going to be just like we threw the ball straight up with this amount of acceleration. So we can find the vertical component just by knowing that it changes by this much, or 10 meters per second, every 1 second. So it starts out at 30 meters per second, then 20 meters per second, and this is our vertical motion, just like we threw it straight up and down. 10 meters per second, 0 meters per second. Now we're filling in our horizontal component. It's going to stay exactly the same, 5 meters per second. 5 meters per second. No vertical here at all. Then going back down, negative 10 meters per second, negative 20, negative 30. We're now going to use the Pythagorean theorem to find this velocity vector. The velocity vector we get when we add the horizontal and vertical components. We'll do this on the way down. So this v here then equals the square root of the x component squared plus the y component squared. We'll go ahead and plug and chug that, and we find that is 11.2 meters per second. The same thing for the next second, but this time it's 5 meters per second squared and then 20 meters per second squared, and we have to take the square root of both of those. We find that's 20.6. And this one goes off the screen a little bit, and it'll go off your page. Same calculation, we get 30.4 meters per second. Let's write the kinematic equations for the case of projectiles close to the Earth's surface when friction is negligible. Notice that the acceleration in the x direction is 0, and the projectile's velocity component along the x direction remains constant. So we basically have distance equals speed times time. To find the speed, we have to go v cosine theta. And for our y direction, we're going to use the acceleration equals g. And that way we can use these 1, 2, 3 kinematic equations that we used before to figure out where we're at along this trip. So what is our problem-solving strategy for projectile motion? First, sketch the projectile path. Resolve v into its vertical and horizontal components. Then we're going to treat the horizontal components and the vertical motion completely separately. The horizontal motion is just constant velocity, and the vertical motion is constant acceleration, and we will use g. So to review, we'll look at vertical motion and horizontal motion completely independently. We'll use our vector components for the vertical and horizontal. The vertical motion is just free fall, just like we threw the ball up and we're catching it. The horizontal motion is constant velocity. All right, complete your Cornell notes, rewind, and review as necessary.